Hey guys, so today we're in section 7.3, which is titled the unit circle, and we'll be covering a few new things, but we did a lot of the legwork in the last section, so hopefully some of this will be familiar. This first page I've kind of done beforehand. I wrote it as a little bit of a reminder of what we did at the end of section 7.2, where we proved the 30, 60, 90 and the 45, 45, 90 triangles, and how we got to the point where we figured out the value of sine of 30 degrees using the 30, 60, 90 triangles and the proportional relationships of which sine are as like opposite over hypotenuse. And with a little bit of algebra over here, we're able to figure out that sine of 30 is equal to 1/2. And with that same sort of algebra, but just for cosine using adjacent over hypotenuse, we were able to figure out that sine of 30 degrees is equal to the square root of 3 over 2, and all of those. So we have sine of 30, cosine of 30, sine of 60, cosine of 60, sine of 45, and cosine of 45 degrees. And we have all of those values figured out. So this section is titled the unit circle. And what is the unit circle? Well, a unit circle is just a circle with radius 1. And all that means is the radius of the circle is just 1. And we're not necessarily giving it a unit in terms of like, is it feet, is it meters? We're just saying it has the distance from the middle of the circle to the outer edge is 1. So you can see no matter which direction I go, because a circle is perfectly round, as long as I start from the center and go outward, the distance is going to be 1. So I've drawn 3 different radii here. The green radius, which is kind of going at an angle, that distance is 1. The red line, which is going directly down, that distance is 1. And the white line going directly to the left, that distance is also 1. So when we're talking about the unit circle, we know the radius is always going to be 1. So here I've inscribed a 30, 60, 90 triangle inside of the unit circle. And because we already know that sine of 30 degrees is equal to 1/2, what is that telling us necessarily? Well, because we're on the unit circle, so sine of 30 degrees, we know that is equal to the opposite over the hypotenuse. And we know the value is 1/2, but because we're on the unit circle, the hypotenuse for this triangle is actually this hypotenuse here, this white line that I'm shading in red now. We already know the distance measurement of that because we're on the unit circle. So that tells us the hypotenuse of any of these triangles, the hypotenuse is always going to be equal to 1. So we can fill out 1 on the bottom here. And because we know that sine of 30 degrees is equal to 1/2, and all we have left is the opposite to fill out, well, we know the opposite has to be equal to 1/2 because 1/2 divided by 1 is equal to 1/2. So we already knew what this was based on the proof of the 30, 60, 90 triangles. We really just needed to fill in the opposite side because on the unit circle, the hypotenuse is always 1. Okay? So the special thing about working on the unit circle, at least for sine and cosine, is that sine of 30 degrees isn't necessarily going to be only just the proportion of how large the opposite side is over the hypotenuse, but because the hypotenuse is always 1 on the unit circle, what sine of 30 degrees tells us actually is how tall the height of the triangle is. And this only works on the unit circle because everywhere else for any other type of triangle, it tells you a proportion of how big the opposite side of the triangle is compared to the hypotenuse. But because on the unit circle, the hypotenuse is equal to 1, on the unit circle, sine of 30 degrees tells you exactly how tall the height of the triangle is going to be. So on the unit circle, sine of an angle, I'm going to call it theta, sine of an angle theta tells us how tall, or the height of the triangle, how tall the triangle is. And in this case, we already know the height of the triangle is going to be equal to 1/2. Cool. So now if we walk to our next picture, and we're looking at this 45, 45, 90 triangle inscribed on the unit circle, well, we already know sine of 45 degrees is equal to the square root of 2 over 2. Okay, and once again, we know our hypotenuse is 1 because we're on the unit circle. Well, we know sine of 45 degrees, well, that's always going to be equal to the opposite over the hypotenuse. But once again, we know the hypotenuse is 1, and we need all of this to equal the square root of 2 over 2. Okay, well, there's only one blank here that we haven't filled in. And so hopefully you can see that if we just put the opposite side equaling to the square root of 2 over 2, we get an equivalence value of, and so look, these two things agree. So, and why does this work? Well, it's because we're on the unit circle, and what is on the unit circle? What does sine tell us? It tells us the height of the triangle. So we know the height of the triangle here is the square root of 2 over 2. Okay, let's move on to the next one. And so now we have a 30, 60, 90 triangle again, but this time the triangle, the angle that we have here is 60, as opposed to, I'm going to scroll back up here, the 30-degree triangle was down here and the 60-degree triangle was up here. So it's just kind of, this triangle is standing up now rather than laying down. And we know from previous information that sine of 60 degrees is equal to the square root of 3 over 2. And so we have the square root of 3 over 2 is equal to sine of 60 degrees. But we know sine of any angle is opposite over hypotenuse. And once again, because we're on the unit circle, we know this hypotenuse is equal to 1. And so we have one blank thing that we don't know, and we can easily figure that out by just letting it be the value that we want to end up with. And so if we let the opposite side equal square root of 3 over 2, that gives us an equivalence value. And so we know, what does sine tell us on the unit circle? It tells us exactly how tall the triangle is, and the triangle is square root of 3 over 2 units tall. Okay, cool. So we just did the version for sine, but this also works for cosine. So we know that cosine of 30 degrees is equal to the square root of 3 over 2. And likewise, so we have the square root of 3 over 2 is equal to cosine of 30 degrees. But we know that is equal to the adjacent side over the hypotenuse. And remember, the adjacent side is the side that's next to the 30 degrees, but not the hypotenuse. And so let me put this, we know this is 1 because we're on the unit circle. So really we're talking about this side of the triangle. This is the adjacent side. And since the hypotenuse is equal to 1, that must mean the adjacent side is square root of 3 over 2 for these two values to equal each other. And so what does cosine tell you on the unit circle? It tells you how large the base of the triangle is. So basically, how wide is the triangle? And remember that this only works on the unit circle because everywhere else, cosine tells you a proportion of how big is the base versus the hypotenuse. How big is the adjacent side versus the hypotenuse? But on the unit circle specifically, which is why it's really nice, is it directly tells you how wide the base of the triangle is. Okay? And so let's do the 45 degree version. So we know that not sine, this time we're doing cosine. Cosine of 45 degrees is also equal to the square root of 2 over 2, which is adjacent over hypotenuse. And so since we're on the unit circle, we know the hypotenuse is equal to 1, and that tells us that the adjacent side must also be square root of 2 over 2, which technically we know from last section. But so that tells us that the base of the triangle is also square root of 2 over 2. And that should make sense because they're both opposing 45 degree angles, and so the distance of them, the height or the length of them must be the same. So that checks out. And now let's go to our 30, 60, 90 triangle, but this time the 60 degree is the 60 degree is here as opposed to being over there where it was in our first triangle. It's just kind of that same triangle in the first part, just standing up. And so, well, we know that cosine, made this bigger on accident. Guess we'll just be stuck with that for now. Cosine of 60 degrees, well, we know that's equal to the square root of 3 over 2, which is equal to adjacent over hypotenuse. And since we're on the unit circle, we know the hypotenuse is equal to 1. And so that tells us the adjacent side must be square root of 3 over 2. Sorry, not square root of 3 over 2. 1/2. And so we know now that cosine of 60 degrees, I made a mistake here. This should be 1/2, not square root of 3 over 2. And so that tells us that the adjacent side is 1/2. And hopefully my little mistake doesn't mess you up too much. You can clearly see that the base of the triangle here is shorter than the height of the triangle. So whatever this value is must be smaller. It can't be exactly square root of 3 over 2 because you can clearly see the triangle is a lot taller than it is wide. So this value is 1/2. And furthermore, what you'll notice is this triangle right here is actually the same triangle as here. It's just that the position of the 30 and the 60 degree angle have kind of changed, right? Here, the 30 degree was on the bottom, and in this variation, the 60 degree is on the bottom. So the main thing that I really want you to take away from this beginning section here is that what do cosine and sine tell us? Well, if we're on the unit circle, sine tells us how tall the triangle is or what the height of the triangle is. Okay? And let me write it here on the unit circle. Cosine of theta tells us how large the base of the triangle is. And this is only because the unit circle has hypotenuse 1. But it's really helpful to think of it conceptually as sine tells us how tall the triangle is, cosine tells us how big the base of the triangle is. And hopefully these images kind of give us a bit of clarity on why that is. When we have the 30, 60, 90 triangle with a 30 degree on the bottom, clearly it looks like the base of the triangle is larger than the height, and these values here agree and tell us the same thing. Here, they're 45, 45, 90 triangle. Well, the base and the height must be the same, and that's also what these values tell us. And here, the 60 degrees on the bottom, so the side opposing it must be larger, which now the height is larger and the base is shorter. So I used it up there, I guess accidentally a little bit, but you're going to see this a lot. So this symbol here that looks like an O, like a cursive O, theta. That's the Greek letter for O, I suppose. And so it usually means angle, but it's just a variable like x. So you may see stuff like sine of x, cosine of theta, and sometimes they may even use like sine of t. So the variable can be whatever it wants, but typically it's standard for us to use theta when talking about an angle. But what I want you to really remember is that whatever that letter is that they use, sine, cosine, tangent, secant, cosecant, cotangent, they take angles as arguments. So you have to give it an angle. So whatever you put in the parentheses in here has to either be a degree, right? Or it has to be a radian. So you can put a radian in here, like sine of pi, for instance. But whatever you're putting in, you're treating it as an angle. So if you don't put the degree unit and you put a number in there, you're saying this is the radian measurement of the angle. So they don't just take numbers. Whatever number you put in, it either has to be a degree or a radian. So how I like to think of the trig functions is they take angles as arguments, so you feed them angles, and what they do is they spit out proportions of triangles. So, for instance, sine is opposite over hypotenuse. Let me rewrite this. Sine of theta. When you plug in something to sine, you're giving it an angle, and what it's spitting out is how large the opposite side is compared to how big the hypotenuse is. Luckily, when you're on the unit circle, we know the hypotenuse is 1, and so whatever's up here is directly going to be what's spit out. So on the unit circle, sine spits out exactly what the height of the triangle is. So if you feed it an angle, it spits out exactly what the height of the triangle is. Likewise, if you feed cosine an angle, it spits out, on the unit circle at least, exactly what the base of the triangle is, what that length is. Okay? Okay, so what I've done here, I've created a little table, and I rewrote the 6 trig functions and their proportional equivalents. So sine of theta, opposite over hypotenuse, cosine of theta, adjacent over hypotenuse. This is kind of more for your reference, so you can kind of see what we're doing here. And so what we're going to do is we're going to quickly fill out this table so that we have the trig values for 0 degrees or 0 radians, 30 degrees or pi over 6 radians, 45 degrees, pi over 4 radians, 60 degrees, pi over 3 radians, and 90 degrees, pi over 2 radians. And so the radians are on the right, the degrees are on the left. And so we're going to have a quick table so that if we're doing problems, we can use this as a resource to kind of glance over and figure out if the question is asking us, for instance, what sine of 30 degrees? We'll have it here on this table. Now, at some point, you're going to want to memorize these because you're not necessarily going to be able to have access on your note on exams that you do in person. So it is really a good idea to remember these because these values here will come back for the rest of your calculus sequence. So through Calc 1, through Calc 2, through Calc 3. We've done this multiple times now, but we already know what sine of 30 degrees is, right? It's 1/2, so we can go ahead and fill this in. And we know what cosine of 30 degrees is. So that's square root of 3 over 2. And so what tangent is. So what is tangent? It's opposite over adjacent. So we're going to come over here, and we're going to do tangent of 30 degrees is equal to opposite over adjacent. Well, so if we come back to our 30, 60, 90 triangle at the top, so 30 degrees, our opposite side, right? Opposite of the 30 degrees, that's going to be 1/2. And our adjacent side, the side that's next to, but that isn't the hypotenuse, is square root of 3 over 2. So for tangent of 30 degrees, we're going to have our opposite side being 1/2, and our adjacent side being square root of 3 over 2. And so you see they both have 2's on the bottom, or we can do the algebra the same way, which is 1/2 2 divided by square root of 3 over 2. And we don't like dividing fractions. Instead, what we like to do is multiply by the reciprocal. So multiply by the second fraction flipped in layman's terms. So now we can cancel the 2's. We get 1 over the square root of 3. And now we rationalize it by multiplying square root of 3 on the top and the bottom. And so we get the square root of 3 over 3. So we have tangent of 30 degrees is the square root of 3 over 3. And I'll write that a little bit neater so that we can see that a little more clearly. Cool. Okay, and now what we want to do is find cosecant. Okay, so to find cosecant, not cosine, cosecant of 30 degrees, well, that is equal to hypotenuse over opposite. And since we know, looking at sine, its opposite over hypotenuse is 1/2, all we really have to do is just flip the fraction. So to find cosecant, it's just 1/2 flipped. So that becomes 2 over 1, or we can just simplify that by writing the number 2. So cosine of 30 degrees is just equal to 2. Okay, I'm going to do secant, but I'll do secant the long way. So secant of 30 degrees is equal to hypotenuse over adjacent, just in case the algebra confused you for cosecant. So hypotenuse over adjacent. So we're going to scroll back up to our 30, 60, 90 triangle. And so our hypotenuse, well, that's 1. It's always going to be 1 on the unit circle. And our adjacent side is square root of 3 over 2. So hypotenuse is 1, adjacent side is square root of 3 over 2. So we have 1 over the square root of 3 over 2. So we don't divide fractions. We multiply by the reciprocal, so that means just flip the second fraction. Well, 1 times anything is itself. So I'm going to write equals down here. So we get 2 over the square root of 3. But we don't like radicals on the bottom, so we're going to rationalize it by multiplying the square root of 3 on top and bottom. And that's going to leave us with 2 times square root of 3 over 3, or 2 root 3 over 3. So 2 root 3 over 3. And then cotangent is just adjacent over hypotenuse. And so since we already know the adjacent side is square root of 3 over 2, and I'm taking this information from up here, and the hypotenuse is 1. Wait, not hypotenuse, sorry. Getting ahead of myself, going too quickly. Cotangent is adjacent over opposite. And we know the opposite side is 1/2. Well, that's equal to the square root of 3 over 2 divided by 1/2. But we don't like to divide fractions. We like to multiply by the reciprocal instead. So now the 2's will cancel, and we'll just get the square root of 3. Cool. So there is the table filled out for the 30 degree. And what we'll do is quickly look at the 0 degree, because that one can be a little confusing. So, well, if we're talking about 0 degrees, and remember our reference angle where we start is usually 0 degrees pointing here. So this is the start. Okay, we technically don't have a triangle at the poles, but what we want to think about is what is the base? Well, so this distance, right, typically that's the base of the triangle. But in this case, it's also the radius, right? We know this radius is equal to 1. So if this distance is equal to 1, and you could kind of think of this as the base of the triangle, this is basically telling us that cosine of 0 degrees is equal to 1, because the base of our triangle is basically the entire triangle. We kind of don't even really have a triangle, but this x value here is going to be equal to 1 because it's the same as the radius. So cosine of 0 degrees is going to be equal to 1. And sine of 0 degrees, well, that's usually the height of our triangle, but since this is our reference angle, we don't have an angle to create a triangle. So we basically have like a flat triangle, like it's been smushed down. So because of that, our triangle doesn't have any height. It's still just stuck on the bottom. So since we have no height, we know that sine of 0 degrees must be 0 because our triangle doesn't have any height. Okay? And so, well, tangent is opposite over adjacent. And so I'm going to show you a little trick with tangent. Well, okay, so tangent of theta is equal to opposite over adjacent, right? Okay, we know sine of theta is equal to opposite over hypotenuse, and cosine of theta is equal to adjacent over hypotenuse. Okay, well, if I write sine of theta over cosine of theta, what do I have there? Well, I have opposite over hypotenuse over adjacent over hypotenuse. And so this is the same as saying opposite over hypotenuse divided by adjacent over hypotenuse. So I'm kind of like dividing fractions, right? And we don't like dividing fractions. We like multiplying by the reciprocal. So that just means change it to multiplication and flip the second fraction. And so since we have hypotenuse and top and bottom, they cancel. And so what are we left with? We're left with opposite over adjacent. Well, what is opposite over adjacent? Well, that's actually tangent, right? So another way to think about tangent is it's just sine over cosine. So, okay, so if tangent is just sine over cosine, we know at 0 degrees, sine is equal to 0 and cosine is equal to 1. So what's 0 divided by 1? Well, that's equal to 0. So we know that tangent is also equal to 0 at 0 degrees. It's a little bit of neat algebra, but it's one of the properties that you're going to want to remember to think that tangent is also can be represented as just sine over cosine. Okay. And since we're doing 0 degrees, let me insert a page here. Since we have, now we're looking for cosecant of 0 degrees. Cosecant of 0 degrees. Well, that is just hypotenuse over opposite. Okay. But also, another way to think about cosecant is since sine of theta is just opposite over hypotenuse, and we're looking for cosecant of 0 degrees, well, cosecant is sine flipped, right? So we can write cosecant of theta as is 1 over sine, because what I mean by this is if cosecant is sine flipped, well, so sine is equal to sine of theta. Okay, that's kind of obvious. But what I'm saying is cosecant of theta is equal to 1 over sine. So you can think of sine as sine over 1 and cosecant as 1 over sine. And so if we know sine here is equal to 0, sine of 0 degrees in particular, so we know sine of 0 degrees, not theta, excuse me, sine of 0 degrees is equal to 0, then cosecant of 0 degrees is equal to 1 over sine of 0 degrees. So 1 over 0. But can we divide by a 0? No, we can't. So we write this as undefined. So unfortunately, cosecant of 0 degrees doesn't have a value. So we write this as undefined. Okay, and so we'll do the same thing for secant. So secant of 0 degrees, we want to figure that out, and that's equal to hypotenuse over adjacent. And since cosine of theta is equal to adjacent over hypotenuse, well, secant is just cosine flipped. So just like we did before, we can think of cosine of theta is equal to cosine of theta over 1. That means secant of theta is equal to 1 over cosine, just flipping the fraction. So then secant of 0 degrees, not theta, secant of 0 degrees is equal to 1 over cosine of 0 degrees. And we know cosine of 0 degrees from the work we just did is equal to 1, and so 1 over 1 is equal to 1. So we have secant of 0 degrees is equal to 1 as well. And finally, we have cotangent of theta. So cotangent of 0 degrees, and that is equal to adjacent over opposite. And we know that tangent of theta is equal to opposite over adjacent. So tangent of theta is equal to tangent of theta over 1. So that must mean that cotangent of theta is equal to that flipped, which is 1 over tangent of theta. So cotangent of 0 degrees is equal to 1 over tangent of 0 degrees, not theta. Keep doing that. Sorry about that. Which is 1 over 0. And so can we divide by 0? No. So this one is also undefined. And so we get undefined here as well. Okay, so I did the 0 and 30 degrees, kind of did that together. If you'd like, you can do the rest of them on your own. And so you can pause the video here if you'd like and try to do the algebra for the rest of them. I'm just going to quickly fill them out. I'm going to pause the video and quickly fill them out. That way you guys have a nice table to use. It'll also be in the book. Let me see if I can find what page it's on. It is also in the book, but let me see. But it won't be given to you until the next section. So I guess I'm giving it to you a little early here, but no big deal. This table is just good to memorize because, like, for instance, on our exams where I state you don't need a calculator, all of our values that we're going to calculate for the most part will be using these values here. Okay, so here's the table filled out for you guys. And I'll leave it here for a few seconds. So that you can check your algebra, check your work, make sure that if you did this on your own, that you got the same values. And so the last part of this section is kind of just going to be a bit of a warning, because in this section there are some problems that have you use calculators. And like I said, we're in an online class. If you have a scientific calculator, feel free to use it. If you're using a digital calculator like on your phone, which can also compute these values, that's fine too. But for instance, if you are using a calculator to find sine of 50 degrees, just be sure that you're in the right mode. So there on a scientific calculator, you might see somewhere on the calculator that says DRG. That's for degrees in radians, and degrees, radians, and gradians, but you're not going to use the gradians. You're just going to switch between radians and degrees. And And so sine of 50 degrees, so I put an example here, sine of 50 degrees should compute to 0.766. So the height of the triangle would be somewhere like just around 0.75 units tall. But if you're in radian mode, but you're trying to calculate 50 degrees and you just put sine of 50 in the calculator, it's going to input it as if you're putting 50 radians. And so the value of that is negative 0.62, excuse me, negative 0.26237485. And so the main thing I want you to take away from this is that clearly these two values are not the same, because 50 degrees, well, what does 50 degrees look like? That's somewhere less than 60, so we'll just say something like that. But what does 50 radians look like? Well, remember that 2 pi is 1 revolution of the circle, right? So it takes about a little more than 6 radians to go around the circle. And so 50 radians is going around the circle almost 8 times. So you'll have to go around the circle 8 times. And where the angle ends up is actually the reference angle for 50 radians is actually only about 15 degrees. So you'll go around the circle, let's say 8 times, and you'll end up at about 15 degrees. And so clearly the triangle that's made with the green angle and the triangle that's made with the red angle are clearly not the same. So that's why these values won't be the same either. Okay? Sorry, it's not 15 degrees, but negative 15 degrees. So this is why the answer is negative. So it would be that angle. So negative 15 degrees or positive 344 degrees, whichever way you want to look at it. So 50 radians has the same reference angle as 344 something. It's not exactly 344 degrees, which puts us on the other side of the circle, on the other side of the x-axis. So clearly not the same degree. That's really what I want you to get away from it. Just make sure that if you're using your calculator to calculate degrees, make sure your calculator's in degree mode. If you're trying to calculate radians, make sure your calculator is in radians, because all you do on a calculator is you just put in 50. You never specify degrees, right? So look for something on your calculator that says DRG, and that's how you change from degrees to radians. All right, and so that's going to be the end of section 7.3, and the next section will be 7.4, so I'll go ahead and post the homework for this assignment on Canvas. All right, see you guys next time.